this is Mr. Walsh, and today we're going to be talking about gas laws. This is going to round out our discussion of Unit 3. We're going to talk about gas laws now because we just got done talking about polarity and how nonpolar compounds can become or are typically found as gases. So here we go, gas laws. So there are three factors that we're going to talk about. There's many more factors than just these three, but these three factors are the major factors that we're going to talk about, and these are the measurable factors that affect gases. Okay, and so we have temperature, which is a measure of how fast molecules move. Okay, so remember, molecules that move fast have a higher temperature. Okay, and we will measure that in Kelvin. Remember, that's a base unit. We go back to our Unit 1 stuff. That's a base unit, and Kelvin is symbolized K. Temperature always has to be in Kelvin in order to do this. Okay. Volume we've talked about previously, but that's the space that the particles occupy. We're going to use liters to measure that, or sometimes we'll see milliliters. Okay. And then pressure is kind of the new one here. These particles will hit the side of the container. This one will hit the top here, and then this one will hit here, then hit the top. You know, they move it all around. They're jiggling, moving, and doing what they can. This is going to hit the bottom. So as they hit, they exert a pressure because of their impact with the side of the container. That impact of the particles against the side of the container is what we call pressure. Okay? And that is measured in atmospheres. That's the kind of the standard unit. It's not a base unit, but that's the standard unit. There are other units of pressure that we'll get to. And so there are three laws, okay? You guys may remember Robert Boyle. He does experimentation, and we talked about him in the history of chemistry. He did experimentation. He modernized chemistry. So Robert Boyle is here, and this is what he did his experimentation on, gas laws, okay? So when we increase pressure, the volume decreases. So imagine, let's see, I have a Snapple bottle right here, okay? And so you can see it from the side. If I increase the pressure on this Snapple bottle, what happens to the volume? The volume goes down. I'm able to decrease the volume, okay? So increased pressure, volume decreases. And we're assuming the temperature doesn't change, okay? That's what we call an inverse relationship. When one goes up, the other goes down. Okay, and so now we're going to decrease the pressure, or what if we decrease the pressure? Again, because it's an inverse relationship, as one goes down, the other one's going to go up. The volume increases. Jacques, I think it's Charles is kind of the pronunciation of that word, but I'm not 100% sure. I know he's French, but I'm going to Americanize it because I'm an ignorant American here, and I'm just going to call it Charles. Okay, so this is his experimentation, and I'm going to take it from this way. I changed this in my own presentation, but okay, I'm going to look at temperature. When temperature increases here, when we heat something up, the volume of that thing will increase. Okay, temperature goes up, volume goes up. That's what we call a direct relationship, when both things go up. Or when one thing goes up, the other thing goes up. Or when one thing goes down, the other thing will go down. Same thing when we make something colder, the volume is going to decrease. Okay? So this is Charles' law. The funniest name in chemistry is Henri. This guy's name was Henri Gay-Lussac. Okay, I think French again, but so I'm not being French, I'm not sure exactly where the pronunciation lies, but I think I'm kind of close. Maybe not. Anyways, what he said is as you increase temperature, the pressure will increase. Now this one is really good. This is another direct relationship, because if you think about a container, like a box that doesn't change volume, well, volume isn't going to change. As the temperature goes up, the molecules are going to move faster. So because the molecules are going to move faster, they're going to hit the side of the container more. They hit the side of the container more, well, faster, more side of the container. So faster is temperature. Hitting the side of the container is pressure. So faster, temperature goes up. side of the container more, pressure goes up. Okay, and then the opposite is also true. Okay, as temperature decreases, pressure also decreases. And again, this is a direct relationship. So here's the summary. You may want to pause this to write this down. What happened is Boyle, Charles, and Gay-Lussac came out with these mathematical representations of their laws. But somebody came along then and combined them all into one big law called the combined gas law. And this is the gas law that we're going to use a lot. Okay. Now let me be explicit here, is that what we are doing is changing the properties of a gas. That's why we care about if one goes up, the other goes down, and when one goes down, the other one may go down, whatever it is. Okay? So we're trying to change one of the properties. So we start off with a pressure, we change the pressure, what's going to happen to temperature? What's going to happen to volume or something? Okay? So this gives us a mathematical way to predict what the change would be, or if we know where it ended, kind of go backwards and figure out where it started. So this is the matter of looking at what's changing and calculating that change. Okay, change in the properties of gases. Okay, so before we do this, we have to convert to Kelvin. Okay, all our temperatures are in Kelvin, so there's going to be a lot of math from here on out. Okay, so if we're going to use Kelvin, I'm going to bring out my calculator here. I don't know if it's easy or hard to see. Let's see. It's a little hard to see, but we can figure something out. Maybe I can do this. Okay. What we're going to do is we're going to convert Celsius temperatures into Kelvin. And to do that, we're going to use this formula right here. Okay? So we put in the temperature in Celsius, and then we add 273, and that's the temperature in Kelvin. So we're going to do this. In order to do this, we're going to do 120 plus 273. Okay. So now we get out our calculator, and we do 120 plus 273, and that's 393. Okay, some of you may be able to do that in your head. That's fine. So now, again, it's the temperature in Celsius plus 273. So we have negative 38 plus 273. Okay, and because this is a negative, it's a little bit different. So negative, it's not different in terms of what we put in our calculator, but just know that your answer is going to be less than 273, so it's 235. 235. So now we get 250 plus 273. Okay. So 250 plus 273. That's 523. 523, and that's K. We're going to put that in K, the unit. Okay, so this is our converted temperature. Whenever we do a calculation, we need to double check that we are in Kelvin. And then the last one, 350 plus 273. So we'll do this. Notice that's 100 more here, so our answer should be 100 more there. So, but we'll still do it. 350 plus 273. Enter. 623. So that's 623 Kelvin. Here's the list of units that you'll see. If it's, like I said, if it's in Celsius, we have to make sure the problem is in Kelvin. Okay? But otherwise, we can keep all the other units the same. You guys are probably familiar with liters and milliliters, so that's what we use for volume. Okay? That's the typical units for volume. And then we have pressure units. And so the pressure units, you should know, are all the kind of the weird units. We have atmospheres, millimeters of mercury. We have this thing called torr. So we have all these weird units. So if it's something you don't recognize, it's probably a pressure unit. Okay. I say all this because we're going to do some sample problems, and we want to make sure that we can kind of pick out, use the units to tell us whether it's volume, pressure, or temperature. So now let's do a sample problem using the combined gas law. Okay. Now, here's the way I would set this up. Okay. Before we even get started, okay, I'm going to list all of these things: P1, V1, T1, P2, V2, T2. Okay. And remember, this is a change. So this is kind of the stuff that happens at the beginning, and this is the stuff that happens at the end. You don't have to write beginning and end over here. But we can go through, and now we can read the problem and kind of figure out where it's going to go. Okay? So it says a gas at constant temperature, okay, has a volume of 240 milliliters. So it says already that this is a volume, 240 milliliters. The gas is reduced to a volume of 60 milliliters. So that's the change, 60 milliliters. If the final pressure of the gas is 2,800 millimeters of mercury, so that's the final pressure. At the end, it was 2,800 millimeters of mercury. What is the initial pressure of the gas? So this is what we're trying to find. Okay. Now, notice temperature is not given. Okay, because that is not changing. Remember, the combined gas law only deals with the things that are changing. So we can do this two ways. Number one, we can read this. Because it says constant temperature, we can get rid of it and not use it in our equation. Or we can go through and find all the numbers, and because temperature wasn't given, we assume that it is constant, okay? Even though it says it up here. Okay, so now what I'm going to do is I'm going to cross this off right in our formula, okay? And so now I'm going to plug in our values. We don't have P1. So I put things in parentheses. That's just kind of how I do, especially for these. Okay, 240, that's our V1, equals P2, 2,800, V2, 60.0. And now we want to solve for P1. Well, how do we solve that? Mathematically, we just divide by each side by 240. Divide by 240. That cancels out, so that gives us P1, and now we do the math. Okay, so let me get rid of this stuff. Okay, so 2,800 times 60.0 divided by 240, and that gives us a pressure of 700, and then we want to make sure we have the right unit. So that unit is going to be millimeters of mercury. Okay, so let's try another one. So again, before we start, we're going to do P1, V1, T1, P2, V2, T2, and we're going to write all of these down. We're going to read the problem and write all of these down. Okay, we have the formula already. Okay. Sample of oxygen at constant pressure. So we have an idea that pressure isn't going to be listed here. Okay? Again, because we're only looking at the things that change in order for the combined gas law. Okay? So it occupies a volume 1.6 liters at a temperature of 364 Kelvin. What will be the temperature of the volume? So what will be the temperature, question mark, when the volume is reduced to 1.2 liters? Okay, so again, we don't have pressure. It says constant pressure, and we don't have data for pressure, so we're just going to get rid of pressure here. Okay, so now what we have is V1 T1 equals V2 T2. Okay, so now I'm going to move this up. Okay, now I'm going to plug it. Okay, what's V1? V1 is 1.6, and T1, 364, equals V2, 1.2, over T2, we don't know, question mark. So here's the thing. So now, if we look at this previous one, notice what we had was multiplication from the get-go. We don't have division. So now because we have division, we have to solve this a little bit differently. And so what I'm going to do is I'm going to cross multiply this. So this is going to be T2. Okay. So what I'm going to do is I'm going to take this. And we used to call this the butterfly method when I was a kid. So I'm going to do 1.6 times T2 equals, and then I'm going to take this part and multiply that, 364 times 1.2. So now if I look at the one that we just did, notice the math kind of looks very similar. Okay. Okay. So now I'm going to divide both sides by 1.6, 1.6. And notice I haven't even brought out my calculator yet. Okay. That cancels, so I get T2 equals, and now I'm going to do the math. Okay. So I'm going to do 364 times 1.2 divided by 1.6. When I do that, I get 273. 273. And then temperature, the unit for temperature is Kelvin, so we're good. Okay? Again, we'll do P1, V1, T1, P2, V2, T2. We'll split them up. It says a gas has a pressure of 3.5 atm. Okay, the temperature of the gas is reduced to, so here's the change. So it started somewhere and it is then reduced to 88.5 Kelvin. So we have to make sure that we do that. This says, what is the initial temperature if the final pressure is 1.00? Okay, so notice it doesn't say anything about constant volume. Okay. It doesn't say anything about constant volume, but volume wasn't given, so we're assuming it's constant, so we're going to get rid of this. We're going to do P1 over T1 equals P2 over T2. We're going to plug this in, 3.5 over T1 equals 1.0 over 88.5. Okay, and now, because it looks like this, we're going to cross multiply. So I'm going to take these two. I'm going to do 3.5 times 88.5 equals, and then I'm going to cross multiply this, T1, 1.00. And now we can do our normal thing here. Okay? So now we're going to divide by 1.00. Divide both sides by 1.00. And so what I get is T1 equals, right? T1's here. So I'm going to do the math. Okay. I'm going to do 3.5 times 88.5 divided by 1. You don't have to divide by 1, but you get 309.75. 309.75. And again, temperature is Kelvin. Okay? So there you have it. This is how you do gas laws. The math can be fun if you give it a chance. So have a great day, everybody.